Okay, so last time, I guess we discussed some very general results on or statements, anyways, for Kähler-Ricci flow, and just some basic theory of this pluriclosed flow. So today I'm gonna prove some of this theorem of Zhao. Giving this proof of Calabi-Yau theorem using Kähler-Ricci flow, and then hopefully also discuss the proof of, where did it go? Yeah, discuss the proof of this theorem that I mentioned last time, that on a torus, the pluriclosed flow always has global existence and then convergence to a flat Kähler metric. And yeah, so I know this this group is maybe not mostly analysts, and I mean, of course, this theorem of Zhao, it's all analytic estimates, but I sort of want to just discuss enough of the analysis to give the flavor and give the ideas for like what we're going to do in pluriclosed flow and then in generalized Kähler-Ricci flow, but not really all of the analysis. So yeah, so the theorem of Zhao is, so we fix M2nj a complex, and G naught some Kähler metric. Sorry, let me. And the key hypothesis, where we're only going to prove part of what he proved. So the first Chern class of this complex manifold is 0. And if we're given G naught some Kähler metric on M, the solution to Kähler-Ricci flow with this initial data exists on a half infinite time interval, so exists for all forward time, and converges to Ricci flat or Calabi-Yau metric. Okay, so this is the this is the theorem, which sort of it's a sort of parabolic proof of the Calabi-Yau theorem, or at least this case of it. Okay. So again, like I said, the proof, I want to sort of show some of the analysis, but not all. But so the first step is as usual performing the scalar reduction. Okay. And well, so in doing this, it seems like I'm going to use the first Chern class vanishing, but it's not really so important yet. I'll say that at the end. But let's, just for concreteness, let's fix omega in N0 form. So this is a holomorphic volume form. And so I have so we have also the initial metric G naught, which determines for us the initial Kähler form omega naught. And let's suppose that U. So I'm not exactly going to derive the scalar reduction per se. I'm just going to sort of impose it as an ansatz. So, but I mean, it suffices to work this way. So suppose U solves del U dt. So U is a smooth function depending on space and time. So del U dt is log omega naught plus I dd bar u to the n divided by big omega wedge big omega bar. Okay. So I'm imposing this equation, and so and then the claim is that what notation do I want to use? I guess omega sub u, and here let me just impose the initial data. U0 is 0. So the claim is that omega u, which by definition is this metric which appeared in the numerator there, that this is the solution to Scalar-Ricci flow. Okay. And so let me just carry this out again, even though it's a very simple calculation, because we'll see some sort of related, slightly less trivial calculations in the generalized Scalar case to come. So we can just directly compute del omega u del t. Well, it's clear. I only have to differentiate this term. So this will be I del bar del u del t, which is then I, just sticking in the equation, I del bar log omega naught plus I dd bar u to the n divided by omega wedge omega bar. Okay. But then using the transgression formula, so this is this famous transgression formula. For the first Chern class. This is exactly minus the Ricci form of omega u plus the Ricci form, well, I could just say associated, excuse me, to this volume form. So I'm kind of overloading the notation, but I can think of the Ricci curvature as the curvature of the canonical line bundle, and then I just need a metric on that bundle, and so omega wedge omega bar plays that role. But of course, since omega is holomorphic, this is just 0, right? So it's exactly giving what you expect. Okay. I mean, alternatively, yeah, I mean, you can just do the calculation locally using that omega's, that big omega is holomorphic, okay? So, okay, in any case, the way I set it up here, I mean, you can sort of derive this equation from just sort of back, like sort of reversing this computation and using the maximum principle. But in any case, we can just impose it if we like, and observe that we have indeed reconstructed the solution to Scalar-Ricci flow. Okay.
Could I ask a question?
Yeah, please.
Could you say a bit about what is transgression for C1?
Yeah. So here, let me make that more precise. So we can make it like very general. We can say G and H like two, even just like Hermitian metrics on M are a complex manifold. And well, they induce these induce like volume forms. Well, also I've Kähler forms. Let me maybe call them omega G and omega H, and then I have dVg is omega G to the n, dVh is omega H to the n. And these, of course, I can interpret as Hermitian metrics on the canonical line bundle, and they have curvature forms, right? which so yeah, maybe I should sort of emphasize or say it in a way that will sort of help us when not everything is Kähler anymore. These induce connections on the canonical line bundle, and then they have associated curvature forms which we call rho. And so rho, or sorry, let me go back to red. Rho, maybe in this context of this volume form, will be, say, well, this is the curvature of this metric on the determinant of determinant line bundle associated with the T star. But in this setting, at least, this is actually just equal to, I mean, this is what we previously just called rho omega, which is the Ricci form. Okay. So this follows from some sort of simple curvature identities. And in any case, when you work it out, the sort of characteristic class theory tells you, right, that any two metrics that you pick this rho will represent the same class. That's the first Chern class. And so as a formula, that works out to like rho omega gn minus rho omega hn. Maybe I try to get the sign right. So it should be, I guess, minus I del bar log of this function. Yeah, okay, I think I got the sign right. And yeah, it's just a calculation, right? I mean, these are sort of straight, at least the way I would prove this, these are straightforward calculations in complex coordinates. Like you can write the Chern connection of G down explicitly. You can write then the Chern connection for this volume form, like interpreted as a metric on the determinant line bundle explicitly. And you can just explicitly compute the difference of these two, and this is how it will look. Does that help? Yeah.
So thanks.
I think it's probably good to pin this down, because like somehow when we get to generalized Kähler or Ricci flow, like I guess it is clear in the end what the transgression, I mean, there's quite a bit of subtlety actually to the transgression formula in the generalized Kähler setting to come.
Why is it called transgression?
I've never completely known. I always know it by this name. I don't know. Yeah, it's this like geometric realization of the topological fact that the two curvature forms represent the same cohomology class, sort of. And I don't know is the short answer. In fact, I can't even, I think, recall where I picked that terminology up as transgression formula. But yeah, I don't know it by any other name though. Yeah, I mean, I think in any case, yeah, this formula is written in many places. Maybe it doesn't really get a name a lot of the time. But yeah. Sorry, I don't know. That's not helpful, I'm sure. But but okay, so yeah, so if we can solve this function, then we've sort of equivalently described our metric, described our solution to Kähler-Ricci flow. Okay, and then just as a last remark that I don't want to prove is that the U equation again admits short time solutions. Of course, we already knew that Scalar-Ricci flow admitted short time solutions, but in any case, we could think of it differently, where we could just a priori solve this for some time, and it's equivalently solving the Scalar-Ricci flow. Okay. So it's equivalent to think in terms of this potential. Okay. Okay. So step two is really is really what's going on in the proof is we need a priori estimates for U. Okay. So what is it that we need? I mean, at the very least, we need say the time-dependent metric to be bounded between two background metrics. Sorry, my knots and U's are getting a little sloppy. Maybe I try to be more careful. So we need that the metric is uniformly bounded between, say, between two background metrics, and then we also need derivative estimates for omega U. So we want to show this is in C infinity. So it should be smooth and it should be sort of uniformly positive. Okay. So that it defines a metric.
That's that first line. That's a pointwise condition, right? It has.
Oh yeah. I mean, yeah. This is like the real meat of the proof. I mean, these are the this is like a pointwise inequality of matrices. Yeah. Of positive definite 1-1 tensors. Yeah. Okay.
This is for all time also.
Yeah.
C is independent of time, and so the point is that it just remains completely straitjacketed at each point.
Yeah, this is uniformly in space-time. Mm-hmm. Yeah.
And you're thinking of it as being like the norm of an element, of any element. You choose any vector, non-zero vector, then the norm must be bounded in this way.
Yeah, exactly. The meaning of this inequality at some point is like omega U or
G
X JX.
Oh, okay.
I mean, I have to include the JX.
So it's really like an inequality of functions on the sphere bundle,
if you like. Yeah. Mm-hmm. Yeah.
Okay.
Yep. Yeah. That's right. So yeah, and of course, yeah, the main tool is maximum principle. And so to start, I would say the place where you really maybe see the C1 equals 0 hypothesis is in the first main estimate. So maybe this is like part A, is to estimate del U del T, or the volume form itself. So here, let me just, for convenience, label this thing. How about we label it star? Okay. So we're going to estimate du dt, and the only real trick we have is to differentiate things. So we differentiate star, and something sort of magical happens. So you take d dt of del u del t. This is d dt log omega naught plus I dd bar u naught to the n divided by omega wedge omega bar. And yeah, in any case, it's just it's a short calculation that basically like the linearization of this quantity is exactly the Laplacian with respect to, this is like the Chern Laplacian or just the standard Levi-Civita Laplacian, because everything's scalar, of del u del t. Okay. So basically when you did, this is more or less just like differentiating this volume form. When you differentiate a volume form, you get the trace with respect to g of the time derivative of the metric. The time derivative of the metric is just dd bar u dot, right? The dd bar doesn't change. So the only thing that gets differentiated is this u, and so you get the trace with respect to g. Maybe I just write one more line. This will work out to like the trace with respect to omega of I del bar u dot. Or sorry, let me. That's lazy. Okay. And here, yeah, it seems maybe just like some calculational thing or something, but more generally, when you look at Kähler-Ricci flow, like this will have some sort of extra term. I mean, here really, what I mean by more generally is without C1 equals 0. So without C1 equals 0, this will not be nearly this clean somehow. But we can summarize this as follows. So I'm going to define H to be the heat operator. This is del T minus the Laplacian with respect to the time-dependent metric. So this is like the time-dependent Laplacian or time-dependent heat operator. Okay. And so we can just summarize this as, when you just rearrange it, it's just the heat operator applied to del u dt is just instantly, there's just exactly 0. Okay. So this is like the nicest possible equation. And again, so we sort of discussed parabolic maximum principles, but immediately so immediately from the maximum principle, you get that sup over m cross any interval of existence of the absolute value of del u dt is bounded above by, well, let's just say by some constant, but it would be bounded above by its initial value. This basically depending on like u naught. So it's a solution to the heat equation on the nose. So it's a subsolution and a super solution. And so you get upper and lower bounds. So you get an estimate for the absolute value. Now that looks just like.
Could you say a little bit more about, because this is a time-dependent Laplacian, so this is like a time-dependent, it's a non-linear in time. I'm just wondering how you're applying the maximum principle exactly.
Well, yeah, one can prove a maximum principle. So I think we did discuss this, like it was quite a long time ago now, like 5 months ago or something, but like you can prove a version of the maximum principle where like the operator here on the right-hand side can have, well, it can depend on time. As long as it's uniformly elliptic, it can depend on time. And it can have a time dependence like gradient first order term as well. And it makes no difference. To the proof. But yeah, in principle, we are applying that. And it might seem a little bit fishy because the whole point is to estimate omega naught, omega u, I mean, but then here I am using it in the maximum principle, but the maximum principle is super robust. I mean, like basically as long as omega u remains positive, not even like in a definite way, just sort of, or like in a uniform way. As long as there's just sort of like some lower bound, you can apply the maximum principle to get the required estimate. I mean, yeah, so we can apply it as if it was, it's really no different, as if this somehow were the background metric.
What would it say if you applied it at each time? Like if you, on a fixed time, if you looked at the time derivative of u at that time, right, and you applied the maximum principle just for that time slice, what would it say?
Well, I never quite think of it. Well, I mean, okay, I guess what you say, sometimes you can dig a little deeper, I guess. And I mean, I usually think of it as applying to a solution on, some domain in space-time.
Okay.
But sometimes you can get a little bit of extra juice by like, well, you can sort of sharpen the form of what the maximum principle gives you by, like looking specifically at the time slice where some maximum occurs. But they don't look all that different, I would say.
Okay.
But yeah, sometimes you can get a little bit more out of it. Wait, sorry, yeah, it's hard for me to see the. Yeah, and yeah, this would be the sort of like ODE comparison version of the maximum principle, but the ODE is trivial here. So like more generally, you can have by the maximum principle, you can sort of have some general like reaction term on the right hand side, and then the maximum principle gives you an estimate in terms of the sort of corresponding comparison solution to the ODE determined by the right hand side. Yeah, that's right. Okay, so yeah, here it looks like an estimate of the time derivative. It maybe just looks like some analytic thing, but of course this also has an immediate geometric meaning, right? This is because du dt is this volume form ratio. This is uniform upper and lower estimate of the volume form. The volume form omega sub u to the n, okay? Because exactly del u del t is the log of the ratio of the moving volume form with the background volume form, okay? So as long as del u, so we sort of bounded on the one hand like some abstract like derivative of u, but it also has this geometric significance. Okay, and then so that's helpful too, because then it tells us basically, as long as if we could bound the metric above or below, we'd be in good shape. We would have at least accomplished this one, like the uniform equivalence. So we have like uniform equivalence of the volume forms, and now we need to upgrade that to uniform equivalence of the metrics.
Does this mean that you won't have to do any rescaling when you do the Scalar-Ricci flow?
That's right. In this theorem, yeah, it's like the simplest kind of convergence. This is a on the nose correct statement. I'm not suppressing any like rescaling. Yeah, and that's also a sort of manifestation of the specific geometry, the C1 equals 0. That's right. In all, like in the sort of what's called Aubin-Yau theorem, like when C1 is negative, of course, yes, you have to rescale.
Just out of curiosity, this use of the maximum principle, was that was that in Calabi's original idea, or is it something that came much later after Yau?
Oh well, I mean,
or you're saying that it's used in a different format
in solving these elliptic PDEs is probably at least 100 years old, right?
No, I just mean that this the fact that you can use the maximum principle in the time flow approach, like this.
Yeah. Oh, well, okay. That's easy to answer. No, definitely not. So I mean, well, so yeah. So basically, Calabi proved an estimate that I'll show soon but in the elliptic case, he proved the sort of higher regularity part, assuming the uniform equivalence.
Okay, but he never did this time heat flow thing.
No.
It
Yeah,
was
there was
different.
no
I see.
parabolic approach. Yeah.
Right, I see.
And then in Yao's work, establishing this like uniform equivalence and also establishing the higher order. I mean, like the thing is, Calabi, I guess, basically his ideas that he worked for real Monchamp pair can be adapted very easily to give the higher order estimates for complex Monchamp pair. But it was still sort of filled in by Yao. But in any case, Yao's original proof is by the elliptic method, this sort of continuity approach. But and then it was whatever, like 10 years later, sort of right after Ricci flow was first discovered, Cao wrote this paper sort of reproving it using the parabolic approach. And as is usually the case, if your problem can be coherently set up either using an elliptic continuity method or a parabolic flow method, usually the proofs aren't all that different. I mean, of course, I'm personally more a fan of the flow approach, but and I think oftentimes the flow approach is a little bit more robust sometimes, and can offer advantages that the elliptic approach doesn't. But in the end, most of the meat of the proof is about the same. It looks different because you're applying elliptic maximum principle versus parabolic maximum principle, but I wouldn't say it's all that deeply different.
Is there a sorry for the stupid question, but is there a parabolic approach to proving Hodge theory? The Hodge theorem?
You mean like harmonic representatives?
Yeah.
Of course. Yeah, that's how I teach when I teach the class.
Oh, really?
We use the flow, of course. Yeah. Of
Is there any text that actually does
In fact,
that?
that's one of the original proofs, as I understand it.
Oh, really?
I forgot who, but yeah, I think my understanding is one of the original sort of definitive versions of the Hodge.
Like Weierstrass or something.
Yeah, uses the parabolic flow.
Ah, interesting.
Yeah.
Okay.
Yeah. They really are sort of quite equivalent methods most of the time. And of course, again, if anything, to just further beat the drum for flows, right? I mean, there's no like elliptic Ricci flow, really. Not really. There's nothing. There's no sort of equivalent continuity approach that can give anything remotely close to what Ricci flow can give. In general, for what I'm saying here, of course, definitely you can. But like outside of the C1 equals 0 Scalar case, like for like more general Ricci flows and stuff, there's no sort of elliptic version of that, at least that I know of. But yeah, no, it's good. Anything else? Okay, so yeah, the main part that I want to skip, maybe I'll relabel this, or yeah, part A was UDT. So part B is to get the C0 estimate for U. And it might seem strange why didn't I like do this first, but in the parabolic approach, this kind of needs part A. But this part I'm almost entirely, well, I am going to entirely skip it. So this uses part A and Moser iteration. What's called Moser iteration? And yeah, so the Moser iteration method, this was one of the big like breakthroughs of Yao in the elliptic case was to use this Moser iteration technique to get exactly a C0 bound for the potential. And basically what you need to make that work in the elliptic case, this is one case, I guess, where the elliptic case is a little bit easier. You need to know that the volume form is sort of under control to make it work. And that's sort of given to you in the elliptic approach, whereas here you sort of need this estimate from part A to know that the volume form is under control. But once the volume form is under control, one can apply this Moser iteration technique to get the C0 estimate for you. So yeah, I'm going to completely punt on this. It's not, I think, all that suitable for a seminar like this. But what I will say, I just want to make one remark. If we only cared sort of about the behavior of Scalar-Ricci flow, um, and not sort of a priori proving Calabi-Yau theorem, there would be an easier proof. So if we already knew omega wedge omega bar was the volume form of some Calabi-Yau metric. So in other words, already assuming that you know you have a Calabi-Yau metric, and then we express omega u as against this Calabi-Yau metric as follows. So basically, if we could set up our potential relative to the known Calabi-Yau metric, it follows immediately from maximum principle. Applied to this equation star. So anyways, let me just go back up. What I'm saying is essentially, yeah, if we knew, let's just say omega naught was already Calabi-Yau, and I could express this down here as like the Calabi-Yau metric to the n or something like that in the denominator, then it's just an instant maximum principle argument to get that u is bounded. But anyways, it's a little bit technical, this part, but I mean, Zhao's original paper does a nice job explaining the Moser iteration. Okay.
What do you mean by C0 estimate?
Yeah, okay. I mean, how about the supremum over some space-time interval of existence of a magnitude u is bounded. So yeah, so uniform bounds above and below.
What is T in this context for B? Like,
yeah, okay. So yeah, when I say these estimates, what I basically mean is assume it exists smoothly on some open interval of that form. Then one will have the following. Well, one will have the estimate claimed, and if there is any t dependence, I'll make it precise. So like for instance, here there's no t dependence. There's no t dependence.
Okay, so assuming that this is that's what it's meant by a priori, assuming that the solution is smooth and well defined up to any time t, this will hold.
Exactly. Yeah. And it's there's this usual sort of analytic circle that you have to sort of say something about right at the end of the proof, where you say, well, okay, this general theory tells me I have some little epsilon time where everything is smooth and I can solve it. These a priori estimates tell me, well, as long as I have a smooth solution, I have certain control.
Yeah.
And then you just say, well, did my flow stop at some finite time t? No, it didn't, because I have all this a priori control. Everything just extends smoothly to time capital T. I can apply the short time existence theory. I extend past time t. And then the a priori estimates hold on the bigger time interval.
Now, Moser iteration, I'm very familiar with it in working, like proving something in a neighborhood of a point, and then what you end up proving is that the solution exists on a successively smaller neighborhood, and then you need to show that there's an intersection, a non-zero intersection. Is that so? What is the iteration here over, like in this case?
Yeah, this is like iteration through Sobolev spaces. So you so like the yeah, so maybe I could write down like the initial stage of it, but it's like you can get like an L2 estimate for you in terms of an L1 estimate, sort of using these facts, like using that you have control over the volume form of u, together with the sort of crucial, I guess there's sort of two crucial ideas at the bottom of it. So I mean, yeah, it's using Sobolev inequality, and it's using control of the volume form. But also crucial is like the pluri subharmonicity. I mean, I guess maybe making it out to be more than it really is, but all I mean here is just that like omega plus omega naught plus I del bar u is positive. That's all I mean. Like somehow these three things are crucial in the proof.
But basically, you're saying that you have a bound in some Sobolev space, but you really want it in another, and so you have to go through somehow a sequence of steps and
yeah, exactly,
improving the bound or something.
Yeah, that's exactly right. Yeah. I mean, I guess maybe when I circle back to, I don't want to make a hash out of it. But maybe
No,
like
it's
when we
okay
come
if you
back
want
to
to
look at
assume it.
general
Just
Taylor-Ricci
sorry.
stuff, sorry.
No, sorry. I mean, I don't want to pry into the part B. If we're going to assume it, we might as well just.
I mean,
assume it.
it's a fairly delicate thing. But well, yeah, it's this bootstrapping procedure basically that you do. You get an estimate in some LP space, and then you use the equivalence of volume forms to sort of in any case, maybe I'll show you next time. I can actually prepare to do it well, because if I do it badly, you'll end up more confused, probably. But okay, so we have this C0 estimate for you, and then also this estimate for the volume forms. Okay, and then C, we can try to get the upper bound for the metric. Okay. And once we have the upper bound, we immediately get the lower bound because the determinant is controlled. Okay, and it's positive definite. So so to do this, again, we basically have no choice. So so we can try to estimate, say, the trace with respect to the initial metric of the moving metric. Okay. So somehow this is positive. And if it's bounded above, then omega u is bounded above by omega naught, by some constant, right? In this matrix sense described wherever I described it. Yeah. So if we want to prove like this upper bound, it suffices to get an upper bound for this trace. Okay. Sorry, let me zoom back in. And then, so yeah, so the form of this estimate for del u del t, right? How did we get it? We got this key equation h del u del t is 0, where h is this time dependent heat operator. Somehow this is like the linearized operator associated to the equation, and every associated quantity will satisfy some kind of reaction diffusion equation where this h is like the relevant operator. So the main thing you have to compute, and again, I'm going to suppress a lot of computations. They're very straightforward things. So I want to apply the heat operator to this quantity I'm trying to understand. Okay. And you have to do a bit of work, but what you end up with is bounded above by some constant times the following. So some constant times trace omega naught omega u times trace omega u omega naught. Okay, so so here, just to make sure it's clear, this is that these are not the same term, right? So this is the trace with respect to the background of the moving, and this is the trace with respect to the moving of the background. Okay. And you can actually take this one step further. Maybe I just pause for a second, right? So in any case, this clearly has some sort of nonlinearity, right? That is, you can't really control in any naive way. But you can take this one step further to simplify things and take a log. And again, I'm suppressing some estimates here, but this will be bounded above by some constant trace with respect to omega u of omega naught. Okay. So these are some computations, okay, with a little bit of estimating. Okay, but mostly it's a computation. And then again, yeah, so from a sort of naive maximum principle point of view, if this is all you were going to do, you would be sunk, right? Somehow, from a very naive standpoint, the correct comparison ODE would be like df dt is like e to the f, right? Or sorry, it's not quite like this. Well, I mean, I guess you can sort of convert this into a term of this form using the control over the volume form. But in any case, well, okay, let me just instead just say it's something nonlinear in f. So you can't really expect any kind of uniform control, right? Because this is just not good enough. Okay, but then there's a standard trick, which again, this sort of came up earlier when I was emphasizing the sort of holy grail I was after in terms of like the potential theory for generalized Kähler metrics. So there's this standard trick, which the farther I get in studying PDEs, a fully nonlinear PDEs, this trick is remarkably ubiquitous. I mean, it seems like some stupid computational thing, but it is like I can't emphasize how important this one trick is. So this is what you do. So the trick is to, well, let me say it in the following way. Is let's also, first of all, consider the heat operator applied to the potential itself. Okay. And what do we get? So the heat operator applied to U, well, this is ddt minus the U Laplacian of U. And du dt is du dt, and that's fine, that's bounded. Okay, this is fine, this is bounded. And then minus, how can I understand this Laplacian? This is trace omega U of I dd bar U. But then here's the magic, right? This is where like a lot of this nonlinear structure gets sort of magically disappears. So you just replace, you sort of use the geometric interpretation of I dd bar U and just say, well, this is omega U minus omega naught. Okay. So I didn't do anything. This is just like basically the definition of omega U, right? And then this, this kind of nonlinear trace term here just becomes an n, right? That's just the trace of a metric with respect to itself. So this is del U del T minus n plus this sort of mysterious term that showed up before, trace omega U omega naught, right? And this is good because, again, just for emphasis, we already showed that this one is bounded uniformly in space and time. Okay. And we also know that U is bounded. So it's like we had this bounded quantity, and then we applied the heat operator to it and managed to squeeze out this nice term that carries a lot of the nonlinear structure. Okay, so well, that per se is not exactly the trick. So that's the key observation, and then the actual estimate. Let me just sort of box this off somehow. So we consider some new quantity phi, which is log trace omega naught omega u minus some big constant a times u itself. Okay. And then all I have to do is put together, so this is like star 2, this is star 3. If I just put these two together, you immediately obtain the following. You obtain that the heat operator applied to phi is less than or equal to, well, the log term contributes some constant times trace omega u omega naught, and then minus a times, again, I'll just put, this is some other constant, maybe C2, C1, whoops, plus trace omega u omega naught. Okay. And then what we get then is, this is bounded above. So I'm just going to pick, I have these kind of indeterminate constants flying around the proof, but you just pick a large enough so that this term will swamp this one. And we could say, for instance, this is less than or equal to negative, say, a over 2 trace omega u omega naught, and then plus, say, okay, I guess the way I wrote it, I kind of presupposed like a sign on this term, which it doesn't have. Anyways, let me just add a negative sign there. The point is, it's you can't really control that term. So let's just say plus C2A. Okay. And yeah, so how you can argue now, well, let me just state the conclusion and then state how you get it. So it's a little bit more involved, but it's still just a maximum principle applied to this inequality, which tells you that the trace with respect to omega naught of omega u is bounded above by a constant which like depends on u. I mean, it can be made much more precise than I'm making it, but maybe this is good enough for now. And basically the way you argue is at a large enough maximum for phi. So if phi gets very large, well, we know u is already controlled. So the only way phi gets large is if this trace is large. And then you can also argue that because the determinant is controlled, if this trace is large, then actually this sort of inverted trace is also large. And so in any case, it requires a little bit of like algebraic trickery, but more or less, like if phi if phi gets too big, then this term will swamp, and this right hand side will be strictly negative. Okay.
I'm just wondering, when you have these operators like omega naught inverse omega u, or omega u inverse omega naught, right? So those operators, those would be like endomorphisms of the tangent bundle, and they would have eigenvalues. And here you're computing the trace or the inverse trace, as you called it, right?
Yep.
And then you also have the determinant. Do you ever have the things that are in between the trace and the determinant?
Yeah, of course. And for certain PDEs, studying the other elementary symmetric polynomials is a fruitful thing to do. Yeah.
But here, it's you don't get that. You only
Well,
have the trace
yeah,
and the determinant.
for these theorems, for like the Monge-Ampere theory, by and large, as far as I'm aware, you just don't need to. I mean,
Is there any kind of theory behind that in terms of like the fact that this is Monge-Ampere means that we're going to need to use these combinations of the traces and so on? Like, is there some?
I don't think it's exactly like that, but on the other hand, these techniques, this like style of estimate is ubiquitous, and it's to the point where it does almost feel like a forced move in the game.
But the point is that you can't. There isn't a way of getting the inverse trace from the trace, but there's also not a way of getting the inverse trace from the trace and the determinant. They're kind of independent to some extent.
No, okay, wait, yeah, well, that's easy to answer. So, well, maybe what I've written doesn't help. So, like, yeah, so well, we know in context by now the determinant is controlled. They're positive matrices. So once it's bounded above, it's instantly bounded below, right? Like the eigenvalues can't go to 0, or else it would drag the determinant to 0. Right? And vice versa. Once it's bound, if you a priori knew it was bounded below, you could also get that it's bounded above. Now, having said that, you can also, so here I did some analysis, right, to claim an estimate for this trace, and then I just say, well, algebraically, I get the lower bound. You can also just apply the analysis to the inverse trace,
right?
Well, I mean, and it's almost, the argument is almost identical. In fact, in some ways, maybe even easier. I don't know. It's just, this is classically the way it's done. But you could also just estimate the inverse trace directly. Yeah.
But actually, so the individual eigenvalues, you don't actually care about them. It's only the trace and the determinant.
Well, I do care, but I like, yeah, because in the end, we are getting, of course, yeah, like we are getting
right. I see.
control over everything, but like we get there implicitly. We get there just by controlling these two scalar quantities. So like the other thing is, in general for these things, I mean, one could attempt a sort of like tensor maximum principle of the matrix omega u inverse omega u, or sorry, omega not inverse omega u, or something like that. Like one could do that, and for certain equations, certain situations, that is a useful thing to do. But
okay, so basically you're getting at the eigenvalues through the determinant, the trace, and the trace of the inverse eigenvalues.
Even just the determinant and the trace alone already gives it. But yeah.
So it's some kind of like arithmetic geometric mean inequality that you're using.
That's exactly right.
I see.
Yeah, exactly. That's exactly right. Okay, so yeah, yeah, maybe I just write one more line. So this maximum principal argument gives you like an estimate for the trace in terms of u, but of course u is already bounded, so it's just uniform. And then so yeah, so as we just sort of discussed, this completes now. So this is the end of I lost it here. This is the end of the proof of this uniform equivalence of the metrics, right? So again, just to recap, like we got the determinant uniformly under control, we got u under control, and then we did this trick with this trace quantity to get the trace uniformly under control, like for all of space and time. And so now we have this uniform equivalence of the metrics. Okay.
Why does the trace imply the estimate for the metric?
So yeah, let's just like
also, what is the definition of the trace? That you take omega u composed with omega zero inverse,
well,
and then
write that. Yeah, like in coordinates, this would be like omega naught upper j bar I, omega u I j bar. Does that help?
It's just omega naught inverse omega u composed. Yeah. It's an endomorphism of the tangent bundle, and you take the trace.
Trace of omega naught inverse omega u. Yeah. So yeah, and then maybe to answer your other question, I just maybe make a very quick remark, right? So like when n equals 2, basically what do we know? It's like you can think at one point omega naught is the identity, omega u is like lambda 1, lambda 2, right? And the volume form estimate is just saying, sorry, this is bounded above and below, right? And then the trace estimate is saying lambda 1 plus lambda 2 is bounded above. And so it's very easy to just sort of, in an elementary way, you can just combine these two things to get that lambda 1 and lambda 2 are both also bounded below. So. Because they're both positive as well. So does that help, Francis? Yeah.
Yeah, thanks. And could you say what part is counts as the trick exactly?
Oh, I just mean, yeah, like somehow this magic little computation that's sort of barely a computation, it's sort of, I always feel like in this Monge pair theory, at least at this part of the proof, this is kind of where the geometry happens or something. I mean, like this is like the convexity of the equation, I guess, if you like, kind of showing its head maybe. Just this inequality that the linearized operator applied to the potential is sort of bounding this term, which is like arising from the coefficients of the equation. I've looked at 100 papers on fully nonlinear PDE, and at the bottom of them, in some form or another, is this observation. I mean, I think it goes in a sense all the way back to Pogorelov kind of. You apply the linearized operator to the potential itself, and it will control some delicate nonlinear term which shows up in your equations. And this is the thing, yeah. So this is the thing which I cannot quite make work in generalized Scalar Ricci flow, and I'll show you guys why in like next week. It's sort of because, well, at least for the commuting case of GK, it's because the equation is not convex the way it's handed to you. It's elliptic, but it's not convex, and you can sort of try this trick, but then you get a mixture of nonlinear terms with opposing signs on the right hand side. And again, I mean, one can think of that as well. It's just some funny, this is just some analytic trick that isn't quite working. You just need a different one. But I do think it's, well, I don't know, that in any case, some kind of idea is needed, I think, for making a trick of this kind work.
When you say that this trick is ubiquitous, I'm just having difficulty imagining what you mean, because here we're talking about traces of operators and.
Well, so yeah, again, maybe just to make some general remark, like you can imagine just some crazy fully nonlinear equation. You could take some very general equation like this and say it's fully nonlinear, and then like L is the linearized operator. Then the yeah, let me just think for a moment. So I'm just trying to think about the most general way to say how it gets used. So in the end, one wants similar kinds of estimates for this. You want to know, is your linearized operator uniformly elliptic depending on, depending on F or something like that, right? And so to do that, you need to apply, and here, I guess I wrote an elliptic equation here. You need to try to control these things. And so you try to control, for instance, maybe like the Laplacian of U. This is kind of like the trace, like the metric trace. And, there's going to be, well, yeah, almost certainly you study something like this, and you will get some sort of nonlinear, some kind of nonlinearity like this. Because I took a log, this is really like a nonlinear term on the right hand side. And then, to actually get control over this, one will need to include L of U itself. And somehow this will bound, excuse me, this will bound, some term kind of this type. Inevitably in these problems. I'm being very rough.
Is that because is that because somehow when you take the linearized operator, or is that just because there are lower order terms in big F which
Well,
which
no,
are
like,
not captured by the
there's
Laplacian?
no
Or?
order terms, right? It's like the cleanest possible fully nonlinear thing. This is not why that's showing up. It's really to do with like the fully nonlinear structure. Like, yeah, like Monge-Ampere, right? You don't have either of these, right? It's just the Hessian itself. I mean, this sort of goes under the name like Pogarelov trick.
But from the geometric point of view, you have no right to apply L to U, right? Because U is in the wrong space, right? It's
right. Well, yeah, I can't decide. This somehow at the intersection of the geometric part and the purely analytic part. It is simply something that works, but I don't think it's I mean, it's sort of, like I said, it's kind of a manifestation of the convexity of the equation, which is stronger. So it's like convex in the matrix variables. And as I'll show, like the generalized Scalar-Ricci flow, like in the commuting case, it's parabolic, it's not convex. And this non-convexity is somehow what messes with this method. And there are, well, yeah. And not only is it not convex, so there are some equations, there's a lot of fully nonlinear theory on equations which are like not convex, but maybe like log convex. If you further take a log, you get convexity. And then basically you can still, that becomes more of an analytic thing. You can really just sort of push harder on the analysis and make it work. But here it's really mixed convex concave. So exactly like, so of course, this like splitting of the tangent bundle you get in the commuting case. So basically the equation is like elliptic on the plus planes, and it's, it's convex in the plus planes and concave in the minus planes. So you get this mixed convex concave structure, which like breaks this whole Pogarelov trick in a bad way. Now, having said that, in the symplectic type case, it does appear to be convex. But on the other hand, what I was saying, the sort of problem was, you can kind of see right here, like this sort of trivial step of replacing del bar u with the difference of metrics is exactly using that I can describe the time t data, that's omega u, in terms of like some differential operator acting on the function and purely background data. That's as far as I can tell the thing which maybe is not quite holding in the symplectic type GK. It's not quite that strong, I think, but anyways, maybe we can talk more about that. Okay, so what time is it? 2:17. Okay, this is fine. I think probably I'll just say a bit about how to finish the proof, and then I guess we'll stop. So we got the uniform estimates for the metric. So the metric itself is controlled above and below, but now we have to show it actually stays smooth. Okay, and this is well, there's some nice geometry here, which again we'll come back to with the pluriclosed case. So so I guess this is part 3. So this is the higher order regularity. And this is due to like sort of Calabi and Yau sort of independently, kind of. So and the point is, and again, I just want to sort of emphasize the geometric content. I mean, I think the way these originally appeared in these papers, it was just, here's this brutal calculation and here's a maximum principle which follows. But the point is there is a geometric significance behind what you want to estimate. So the sort of next higher thing to estimate would be like a third derivative of u, which is like one derivative of the metric. But of course, the sort of geometrically meaningful quantity, which is sort of at that level, is the difference of Chern connections. So epsilon omega u omega naught, by definition, will be the difference of Chern connections. So this is the Chern connection associated to omega u minus the Chern connection associated to omega naught. Okay. And then the sort of magical.
This is the Chern connection on the tangent bundle or the canonical bundle?
Oh yeah, on the tangent bundle. So this is a section of like wedge 1, 0 tensor and endomorphism of T1, 0. Yeah, this is like the full Chern connection. Yeah, on the tangent bundle. Mm-hmm. So the sort of, well, so yeah, this certainly seems like a reasonable quantity to measure the third derivatives. And then on top of everything else, you want to sort of take its norm with respect to the time-dependent metric. So you apply the heat operator to the magnitude of epsilon squared. Let me not write the omegas. And then I take its norm with respect to omega u. Okay. And then again, yeah, the sort of totally amazing thing is that this is bounded above by a constant depending on, what's the simplest way to write it? So this is a constant depending on, say, lambda, where lambda is the constant governing this uniformity. Let's just say it like this. Okay. Okay. So a priori, one would expect, all kinds of, I don't know, sort of worse nonlinear terms on the right-hand side. But it turns out that this thing sort of, when you apply the heat operator to it, it drops order in a sense, and you only see things involving like the C0 data of the metric. So I'm using like the term C0 in a different way. In any case, it's just using this uniformity of the metrics. That's all you need to control this right-hand side. And this is kind of, it's a sort of fairly astounding cancellation of various nonlinear terms. But, and again, here is something where if you maybe nudge the equation a little bit, you're not getting something nearly as nice on the right-hand side. So this is definitely sort of using some magic of the geometric situation. Okay. So yeah, so yeah, and then again, we can just, so despite this term on the right-hand side, it's easy to sort of apply a few maximum principle tricks to show that the supremum over space and time of the magnitude of epsilon is uniformly bounded above. And yeah, I mean, in any case, yeah, you have to worry a little bit about this term to make it actually uniform in time, but the test function you can use is something like t t norm epsilon squared plus some large constant, say times the trace or something. So in any case, it requires just a little bit of, this is just some little trickery to get rid of this constant term. And then what you can show is if this is phi, you can show that the heat operator applied to phi is less than or equal to, I guess again, some constant, but then you just apply this on short time intervals and you get a uniform estimate for this epsilon. Okay. Because we know that this trace on the right-hand side is already controlled.
Sorry to repeating this question, but the fact that the supremum is bounded by C, but the fact that C doesn't depend on T, like I kind of want it to get smaller for small t, no?
Oh, that's later. You're saying to actually prove a convergence.
No, I just mean that that, you know, if you flow, like what does this tell you about epsilon squared? I mean, it's saying that after you flow for a certain time t, then it doesn't blow up anywhere along that interval, but somehow I would like to know how big epsilon gets, like how quickly it gets big.
Well, I mean, but this is saying it never does, right? I mean, this is saying no matter how long the flow goes, it will stay in some controlled like ball.
Okay, I see. So it doesn't remain bounded for all time by the same bound, but it's.
No, it does. It does. When I'm saying C, I'm careful here that the C's do not depend on time. That's key. Yeah.
Oh, okay. So I misunderstood. Okay, right. Okay, good.
Yeah, no, they're uniform in time. That's key. So yeah, this gives yeah, so this gives like you can either think of it as a C3 estimate for
Oh,
you.
and sorry, in respect of what you said about C3 just now, this thing is not really a third derivative. It's actually like a difference function, right? It's taking epsilon at t minus epsilon at 0.
Yeah. Well, yeah.
Or sorry, so, the difference between the Chern connection at the end and the beginning of the interval.
Exactly. Yeah, that's right. And so yeah, it's a little bit strange because yeah, it starts at 0. That's true. I could have picked any background metric, not the initial one along the flow. That's sort of not the point. Yeah, I suppose that's a little bit misleading.
What about taking the derivative of the Chern connection? Just nabla dot. Nabla dot would be an endomorphism value of one form.
You want an actual like tensorial measurement of the third derivative. Like,
no, but if you take the nabla dot, that's an endomorphism valued one form.
Yeah. I mean,
that's not sufficient.
Estimate that along the flow.
Yeah,
you can do that too. I guess that's like estimating the derivative of curvature, like epsilon dot or nabla dot will be like one derivative of the time derivative of the metric, which is Ricci. I mean, I guess let me just back up.
Like, I see.
The reason for studying this epsilon is like, you basically want to just measure the third derivative, but you want to do it in a sort of geometrically natural way. And so the natural way to do that is as a difference of connections. That's, a priori defined. That's a perfectly fine tensor. And then I want to take its norm, and I don't want to take its norm in any way. I want to use the sort of flowing metric. This is key. The whole thing is a nightmare if you don't do this. If you don't use metric omega u. Sorry, did you ask something, Francis?
Yeah, sorry. I was asking, in what sense is this measuring a third derivative?
Yeah, so the Chern connection locally, right? Or I mean, these are just Levi-Civita connections, really, right? it's like expressed locally in derivatives in terms of like one derivative of the metric, and the metric is two derivatives of u. So it's like a third derivative of u, or it's like one derivative of the metric. So yeah, so like this tensor is a reasonable measure of this third derivative, and then this norm with respect to omega u is the right scalar way to just measure all third derivatives at once in boxed into one scalar quantity. And then the sort of miracle is that you get this clean maximum principle.
But there's no how this, you called it a magical fact, but I mean, why does it? How are we supposed to know that this thing? How would anyone have guessed that this is the way that you should measure it in such a way to get the maximum principle?
There's a reason he won the Fields match, right? I mean, like, I don't know, like,
but there isn't a theory behind it, like, which guides you to this answer. I mean,
I think it's sort of, this is like the birth of geometric analysis, is using the geometrically natural norms to measure the geometry itself is the right way to proceed. I don't know.
But some of what you wrote is choices which don't affect the result, right? Like, you didn't have to use nabla. You could have used. I'm guessing that there is some freedom, but the point is that you may have guessed to measure it with respect to the background metric, and you're saying that would lead nowhere.
Yeah, it would lead nowhere, but also, like, the thing is, right, like, think about it this way. Once you're sort of committed to the idea of like geometrically natural operators and quantities, we already know what the linearized operator is, right? It's the heat operator with respect to omega u, the time dependent omega u. So think about it. I have to pass that through some
I see.
Surely using omega u is the way to go.
I see.
Right? To like greatly simplify. I mean, if you're just thinking in terms of tensorial operations, it's sort of, why would you ever do anything else? It's sort of obvious that you should do this.
I see.
But then part of the miracle of like the Scalar-Ricci flow is that, of course, then you also have to take the time derivative of these metrics. So some extra Ricci terms show up, but then those also sort of cancel out in a nice way. But again, like, if you look at these very old papers of like Calabi and Yao, it's presented as this brutal calculation where like nothing is a tensor. But now you can boil it down to like a handful of lines where everything, if you really just use like tensor calculus for everything, it's way easier. I mean, it still seems slightly miraculous, but it's
and the maximum principle, whenever it is used in these techniques, there's only a scalar maximum principle. Is that right?
No. Well, no. And of course, yeah, for this proof, everything's a scalar maximum principle. But but these tensor maximum principles are a big deal for Ricci flow, for sure.
I see. Okay.
I have yet to make any such tensor maximum principle work for like pluriclosed or generalized scalar. But again,
this is for the Laplacian on forms, or is it a different notion of maximum principle?
You're saying tensor maximum principles.
Yeah, if it's a tensor maximum principle, I mean, I don't know what those are, but presumably it's using the Laplacian on forms.
The first result about Ricci flow is this paper of Hamilton, where he classifies manifolds of positive Ricci curvature, right? And basically the first sort of estimate, the first key geometric fact in the proof is that positive Ricci curvature is preserved, right? And that is a tensor maximum principle. He developed, you apply the maximum principle to the symmetric matrices.
Okay.
Or symmetric two tensors.
I see.
Yeah.
Okay, thank you.
Yeah, sure. So yeah, I guess it's getting a bit late. But maybe I just wrap up in a few words. So this is a C3 estimate for you, or equivalently, it's like a C1 estimate for omega u. And here you can appeal to various ways to complete the proof. So you can apply these classical Schauder estimates. So by now we can think of the equation for U as parabolic with C alpha coefficients. So Schauder estimates can give that U is like uniformly, not U and C infinity, let's just say U has a uniform C infinity estimates. Okay, so you can indeed get the global existence. Now the convergence, yeah, I also had mostly, or maybe I should just take a breath. Yeah, this is the end of the existence part of the proof. Okay, we were like sort of right at the finish line there. Yeah, and then so I guess part 4 is convergence, and yeah, I mostly want to skip this. It's definitely purely analytic at this point. So the proof Tsao gives uses this Liao estimate. So basically, at this point, you can think of the equation for U, even though it's a fully nonlinear equation, we've controlled everything well enough that you can pretty much think of it the same way you think of a heat equation, and you can get that U converges to some limit, a U infinity. Alternatively, a bit more maybe geometrically, but kind of less sharp or something, you could appeal to this Perelman F functional. So what do I mean by this? We by now sort of any quantity you like is controlled. The geometry is fully controlled all the way out to time infinity, and you know you have this monotone functional, and so it's sort of a standard argument to show that at least some subsequence will converge to a critical point of the functional. And then you can, again, through some analysis, sort of upgrade that subsequential convergence to a genuine smooth convergence of the whole flow line. So yeah, in any case, there's work to do here, but at this point, it's sort of a pretty much of a purely analytic nature, I would say. So yeah, I think probably that's a good place to stop. So next time, so I had hoped, next time I'll discuss this proof of showing the pluriclosed flow always converges to a flat metric on tori, and maybe just to sort of set the stage. In a sense, we follow some ideas in this proof, but a lot of it has to be a lot different. So for one thing, in the pluriclosed case, you don't even have a potential. So your metric is not described by one function at all. It's just not that rigid. And so this is like completely out the window. And this is, of course, why we have to make a much stronger restriction that we're on a torus instead of just being on a Calabi-Yau, on a C1 equals 0 manifold. But nonetheless, we can still get some upper and lower control over the metric by just like looking at maximum principles for quantities of this kind, and then using the sort of strong background geometry, we can just sort of ignore these nonlinear terms. And then the part I really want to get to and show you guys is actually this higher order regularity step. So here, you know, the point was to study the difference of the Chern connections. And the sort of the key point in getting the higher regularity for pluriclosed flow is to basically study the difference of Chern connections associated to what's essentially a generalized metric on T10 plus wedge 10. So basically you write down what looks like the B field transform of the GG inverse metric, where B is a certain torsion potential. And that thing, that's a Hermitian metric on T10 plus wedge 10. That thing has a Chern connection, and then you sort of look at this upsilon type quantity, and again, it sort of miraculously satisfies a Sharp maximum principle. So this was actually the thing which convinced me that I was never going to understand this equation until I understood generalized geometry. So was basically finding this estimate. So, but yeah. So anyways, that's what I'll do next time, I suppose. Are there any more questions? Thank you.
With this Perelman functional, is I guess it's more clear where does the flow converge. But what happens with this Li-Yau estimate? Do you get any control on what vortices.
So yeah, so with the Liao, what you end up proving, so you have to go. Let me just go back up here. It'll be easier. Where did it go? Yeah. So with this Liao, you first of all notice that like this description of the metric allows for a freedom. I could also add like a time-dependent constant on the right-hand side, and I'm actually describing the same geometry. So anyways, what you prove with the Liao is that du dt is like at least converging to some constant. And then you subtract that constant off. Okay, that part maybe is not super important to the analysis. I mean, you prove that du dt up to this discrepancy of tuning this constant converges to 0. And once it converges to 0, it's instantly Calabi-Yau, right? So you've instantly prescribed the volume form of the limit in terms of this background, in terms of this holomorphic volume form. And so it's instantly Ricci flat. Actually, in a sense, the structure of the limit is easier to see with this Liao argument, because when I was saying with this Perelman estimate, a priori, all you get is convergence to you get convergence to a soliton, but then you instantly know that solitons are in fact Ricci flat. Compact steady solitons are Ricci flat. So anyways, it just needs this one little extra geometric argument to say that it's actually Ricci flat. And also, maybe I just emphasize that the Liao estimate sort of instantly gives also sort of like the convergence rate. It instantly gives the sort of exponential convergence rate. Whereas if you want to argue using this Perelman functional, well, you don't get that right away in any case. You at least, I mean, it's sort of a nice conceptual way to think about why it's converging, but actually in the end, it's analytically maybe not as strong. Or in any case, you still have a bit more work after that to get what the Liao estimate gives you sort of right away.
So this Liao estimate, just so that I understand, they're showing everything so far has been bounds, right? So there's nothing that's getting smaller and smaller, which shows you there's a that it converges to something. And so you're saying that they use some kind of symmetry in order to get this?
Oh, no, it's not symmetry. It's quite robust. So so basically the classic Liao is you have like a solution, a positive solution to the heat equation, and then you try to estimate the gradient of log u squared just a moment. So you end up estimating, I guess, t grad log u squared plus, I forget always the precise term, but basically the idea, I mean, you have to do some work, is that some quantity like this should be less or equal to 0. Oh yeah, sorry, I forgot some of the terms. Maybe plus.
I guess maybe the details are going to be lost on me, but maybe the logic hopefully won't. So the logic is something like, like we're going to search for a quantity that we can prove is getting smaller somehow, and they find it somehow.
Exactly. Yeah. And yeah. So yeah, and so like you can see if you could estimate, if you could get like a sort of sharp estimate of this kind, right? So as t gets larger, right? So this is actually providing some decay finally, right? So this is kind of, roughly speaking, the logical structure. So yeah, so the precise form of the terms in the Liao estimate are like weighted by time. And so as long as they're weighted by time and uniformly controlled, then in fact they're decaying in time, right? Like the corresponding quantity without the t will be decaying in time, right? Yeah. So right.
So what are they exploiting? Like, is it clear to you somehow what they're using? It's something new, right? It's not something that was used in the previous estimates. It's
yeah, no, it's definitely like it's what it is. So yeah, I shouldn't have used u here. This was a bad letter to pick, because this u is of course not the u above.
Oh,
I was
okay.
just saying, if you have a solution to a heat equation, I mean, anyways, maybe I just quickly.
You were imagining another context where if you want to prove something about convergence for the heat flow,
Exactly.
you could use this Li-Yao estimate.
Yeah, exactly. And so this Li-Yao estimate is a very strong, sort of very general estimate for like solutions to heat equations.
Oh.
And it gives like sort of sharp decay rates. It's sort of, they basically are like estimating the heat kernel itself.
Oh.
And what Tsao applies it to is you have to go back to the one sort of super clean part of the analysis, which is right here, right? So du dt satisfies, you know, this time dependent heat equation on the nose. Now, of course, you have to like rejigger the Li-Yao estimate because originally they did it for just a fixed Riemannian manifold, right? Whereas here it's a time dependent Laplacian, but in any case, basically it just requires estimating a few extra terms which are already under control. I mean, we already have like the strongest possible control over omega u at this point of the proof.
I see. So I see. So all of the previous estimates go into that exact argument. It's to make the Li-Yao argument work for convergence. Because otherwise,
don't think it's really quite right to think of the proof that way. I mean, it is true that the final convergence step does definitely exploit not just the global existence, but the fact that like the metric is uniformly controlled all the way out to time infinity. It's definitely exploiting that. Well,
why can't existence be a consequence of the Li-Yao? Like if it's converging, how come you can't prove that the convergent? You know,
well, because like I said, to actually get the decay from the Li-Yao estimate, you already need to know that, for instance, like the time dependent Ricci curvature is bounded. You need to just like throw that term away in trying to run the Li-Yao estimate on du dt. And that's like a big, nasty nonlinear term, which only this like previous mountain of analysis has told you, don't worry, it's fine. You know, like you cannot short circuit the proof that way.
Interesting.
Yeah. And maybe it just emphasizes also like most of those estimates, the way they're written is sharp, in fact. I mean, du dt will go to 0. But it's not like the Laplacian is going to 0 or something like that, right? Because like my initial background metric is totally arbitrary, right? I'm picking like basically an arbitrary element of the Scalar class. So like u itself as a function, simply saying it's bounded in certain norms is essentially sharp in terms of like the structure of the proof. The limiting metric, of course, is unique in the end. But if you think about the logical structure of the proof, right, all I know is I just pick some element of the Scalar class, and then I start describing my metric in terms of this function u and that randomly chosen background metric. So like saying it's controlled is the best you can do. Well, for most of the quantities, that it's the best you can do. But in the end, indeed, like del u dt goes to 0. So it is converging.
Do you believe that based on your understanding, which is you know, several orders of magnitude higher than mine, do you believe that it's impossible to have a proof of this theorem which doesn't use a background metric?
No, I mean, I don't know. I wouldn't even know like where to begin. Yeah, the whole story is using this like reduction and yeah, I think, I mean, I would say, yeah, no, I think it's very hard. But on the other hand, I mean, I think the proof is super robust in the sense that like these choices of background metrics are totally arbitrary, really. I mean, it's a very powerful proof, in fact, despite the fact that it is choosing some background geometry, like it's not really using anything significant about them, right? I mean, like the only thing of significance is topological, right? I mean, like we definitely are using the vanishing of the return class.
But to me, those are arguments for why it shouldn't be there in the first place. The fact that it's so robust and that it doesn't really depend on anything to do with the background choices, and the fact that the equation itself doesn't refer to them, it seems weird that it's necessary. But maybe
Well,
Maybe
I
I'm
mean,
just
I think just with the general philosophy of PDEs, where you sort of are looking for something you don't expect to be able to describe explicitly, estimates, a priori estimates are required. And once they're required and you're talking tensors, manifolds, then background choices are required, basically. I mean, I feel like the presence of the background in this proof is really only pretty much just to like make sense of what it even means to measure one unknown metric against a known one, essentially. I mean, I would say the relevance to the proof is that, I guess, insignificant or something. There's just a few sort of subtle places where the topological hypothesis kind of rears its head in sort of in getting this particularly simple form of the scalar reduction, and then in getting this particularly nice equation for del U del T. This is really,
so that equation, for example, is that doesn't require any background metric to explain.
well,
right?
it requires the background volume form at least, right?
Oh, that I'm okay with. Yeah.
But to define the U, you need the background metric, right? So like,
Yeah.
in a sense, it does kind of reference the background.
Yeah. Well, and also, yeah, maybe to emphasize that point, like I set this up like I set up this U equation as if it were sort of in ansatz. I said, well, just suppose I could write it this way, but you can derive it. I mean, you literally can just derive this from the DD bar lemma and the form of the equation.
Sure, yeah.
I mean, it really is there, I guess is what I'm trying to say. It really is like the heart of the actual Ricci flow equation. Is this U equation?
The other thing I mean, related to this question is that there's this paper of Calabi around the same time, which of Yao's proof, which works on the total space of the canonical bundle. So he says let's take any manifold, like not necessarily Calabi Yao, and then you work on the canonical bundle, and you try to which is Calabi Yao, or the anti-canonical bundle, which is Calabi Yao, and then you try to solve the Moser-Iteration equation, which you can write in terms of a scalar quantity now because you are on the total space of this bundle, and what he shows is that depending on the Chern class, you either get a metric on the total space which is invariant, or it might not be complete. So you get just like a neighborhood of the zero section. You get a metric just on the neighborhood of a zero section.
I see.
So it's a kind of natural idea, right? That if you don't if your canonical bundle is not trivial, there's an obvious Calabi Yao sitting right there in front of you. Why not use it?
That's interesting. What is the name of this paper? I don't think
I can send it to you. I have it. I have it on my iPad somewhere.
That's very interesting. Yeah.
At least the analog of that paper should have an analog in the GK case, because we have those anti-canonical bundles.
Absolutely. That's interesting. I would like to see that. Okay, so yeah, maybe that's it. Yeah. Thanks everyone.